Hello students, in today's session we are going to close look at different structure of some simple ionic compounds of the type AX and AX2. This topic comes under the chapter solid state. So let's have a quick revision on basic concepts connected with solid state chemistry, like what are solids, its properties, classification and characteristics like crystal lattice, unit cell, crystal structure, closed pack arrangement and voids. Before moving on to our topic, I have a question for you. What do you think about when you hear the word chemicals? Do you think about a smelly gas or maybe some kind of poisonous liquid? Well, actually everything around us is made of chemicals except light. So, for example, our phone, clock, bottles, pens, toothpaste, almost everything we use daily are chemicals, and the device that you are watching me right now is also made up of chemicals, and the majority of these chemicals are solids. We know that solids are composed of tightly packed particles. They retain their shape, and the constituent particles like atoms, molecules or ions are not free to move about. They can only oscillate about their mean position. So, let us now go further and classify the solids. If you look at diamond and glass, we can see that both are solids, but if you look at them at microscopic level, we can see that there is a difference in arrangement of constituent particles. In diamond, the particles are arranged in an orderly fashion, whereas in glass it is completely disorganized. So, based on the order of arrangement of constituent particles, we can classify solids as crystalline solids and amorphous solids. From the figure, it is clear that the crystalline structure has a pretty neat arrangement and amorphous solids which have disordered pattern. Examples for crystalline solids are diamond, sodium chloride, etc. And for amorphous solids, we have glass, rubber, plastics, etc. Now, let us compare the two types of solids by looking at the table. So, for crystalline solids, we have regular three-dimensional arrangement of particles due to which they have well defined geometrical shape, whereas for amorphous solid, they do not have regular arrangement of particles, therefore, they do not have well defined particles. They have long range order for crystalline solids, they have short range order for amorphous solids. And for crystalline solids, they have sharp melting point, they have high and fixed heat of fusion, they are anisotropic, they are true solids. Whereas for amorphous solids, they do not have sharp melting point, they do not have fixed heat of fusion, they are isotropic and they are pseudo solids. Again, crystalline solid shows two break in cooling curve, whereas amorphous solids show smooth cooling curve. Crystalline solids, they are more stable, whereas amorphous solids, they are less stable. Last, crystalline solids, when we cut with sharp tools, they split into two pieces and newly generated surface are plain and smooth. But for amorphous solid, when we cut with a sharp edged tool, they cut into two pieces with irregular shapes. So, I think the difference between the two types of solid is clear for you now. Moving to our next topic, most of the things we see around us are crystals, or we can say they are crystalline in nature. In today's section, we focus more on their classification and properties. Based on the nature of intermolecular force operating between them, the crystalline solids are classified into four categories as molecular solids, ionic solids, metallic solids and covalent solids. First, we will start with molecular solid. See, these are solid compounds made of molecules, or we can say the constituent particles are molecules. Then we can take a look at ionic solids. As the name indicate, ionic solids are composed of ions in which cation and anions are held together by ion to ion interactions. They are brittle, hard and have high melting point. They will not conduct electricity. Good example which we can think of is sodium chloride. Here Na plus and Cl minus ions are the constituent particle. Well, if we have a network of atoms held together by covalent bond, we are going to produce so-called covalent solids. This is our third type. Here, the constituent particles are atoms and are connected by covalent bond throughout the crystal. These are solids made of carbon or silicon. They are hard and have high melting point. They do not conduct electricity. Last, let us take a look at what is metallic solid. They are made up of metals and are held together by metallic bond. Actually, their constituent particles are ordered collection of positive ions or metallic ions which are surrounded by free sea of electrons, and these free electrons are responsible for electrical conductivity and thermal conductivity. They have rigid structure. Now, let us move on to our next topic, crystal structure. Have you seen a crystal? Yes, you have. So, what is a crystal? Crystal is any solid material in which the component atoms are arranged in a definite pattern. Examples of crystals include diamond, salt, quartz, snowflakes, etc. Okay. Now, if the three-dimensional arrangement of constituent particles in a crystal is represented diagrammatically, in which each particle is depicted as a point, the arrangement is called crystal lattice. Thus, a regular three-dimensional arrangement of points, that is, the constituent particles in space, is called a crystal lattice. The characteristics of a crystal lattice are: each point in a lattice is called lattice point or lattice site, and each point in a crystal lattice represent one constituent particles which may be an atom, a molecule or an ion. Next, the lattice points are joined by straight line to bring out the geometry of the lattice, and when we connect these straight lines, we can get a three-dimensional view of the structure. This three-dimensional arrangement is called crystal lattice, also known as Bravais lattices. And if you observe this crystal lattice, we can notice that there is a small group of lattice point which repeat itself again and again to form an entire crystal lattice. This small group of lattice points are known as unit cell. Therefore, unit cell can be defined as the smallest portion of a crystal lattice which, when repeated in a different direction, generates the entire lattice. So, a unit cell is characterized by its dimensions along the three edges A, B and C. These edges may or may not be mutually perpendicular. In this unit cell, the angles between the edges between B and C is alpha, between A and C is beta, and between the edges A and B is gamma. Overall, a unit cell is characterized by 6 parameters, that is A, B and C, which are edge lengths, and alpha, beta and gamma, which are phase angles. There are 7 possible combinations of A, B, C and alpha, beta and gamma for forming 7 types of unit cells. These are also called crystal systems. There are cubic unit cell, tetragonal unit cell, orthorhombic unit cell, monoclinic unit cell, triclinic unit cell, hexagonal unit cell and trigonal or rhombohedral unit cell. Dear students, please memorize these characteristic properties as they are very important topic for your competitive exam. Now, let us discuss the different types of unit cell. As shown in the figure, the unit cell is classified into primitive unit cell and centered unit cell based on the position of constituent particles. Again, the centered unit cell is further classified into 3 as body centered unit cell, face centered unit cell and end centered unit cell. So, when the constituent particles occupy only the corner position of a unit cell, it is known as primitive unit cell and it is denoted by the letter P. Centered unit cells. When the constituent particles occupy other position in addition to those at corners, it is known as centered unit cell. Coming to the 3 types of centered unit cells, first body centered unit cell. when a constituent particle is present at the center of the unit cell in addition to the particle present at the corner position, it is known as body centered unit cell. It is denoted by the letter I. Face centered unit cell. When the constituent particles are present at the center of each face in addition to the particles present at the corner position, it is known as face centered unit cell. It is denoted by the letter F. Lastly, we have N centered unit cell. When the constituent particles are present at the center of two opposite faces in addition to the particles present at the corner position, it is known as N centered unit cell. It is denoted by the letter B. Now, let us move to the close packed structures. In solids, the constituent particles are close packed, leaving the minimum vacant space. Let us consider the constituent particles as identical hard spheres and build up of three-dimensional structure in three steps. First, a close packing in one dimension. There is only one way of arranging spheres in a one-dimensional close packed structure, that is to arrange them in a row and touching each other. In this arrangement, each sphere is in contact with two of its neighbors. The number of nearest neighbors of a particle is called its coordination number. Thus, in one-dimensional closed pack arrangement, the coordination number is 2. Next is the close packing in two dimensions. This two-dimensional closed packed structure can be generated by stacking the rows of closed packed spheres. This can be done in two different ways. First way is, the second row may be placed in contact with the first one such that the sphere of the second row are exactly above those of the first row. Now, the spheres of the two rows are aligned horizontally as well as vertically. If we call the first row as a A-type row, the second row being exactly the same as the first one is also of A-type. Similarly, we may place more rows to obtain AAA type of arrangement as shown here. In this arrangement, each sphere is in contact with 4 of its neighbors. Thus, the two-dimensional coordination number is 4. Also, if the centers of these 4 immediate neighboring spheres are joined, a square is formed. Hence, this packing is called square close packing in two dimensions. In the second way of arrangement, the second row may be placed above the first one in a staggered manner, such that its sphere fit into the depression of the first row. If the arrangement of spheres in the first row is called A type, the one in the second row is different and may be called B type. When the third row is placed adjacent to the second in staggered manner, its spheres are aligned with those of the first layer. Hence, this layer is also of A type. The spheres of similarly placed fourth row will be aligned with those of the second row, B type. Hence, this arrangement is of AB type. In this arrangement, there is a less free space and this packing is more efficient than the square close packing. Each sphere is in contact with 6 of its neighbors and the two-dimensional coordination number is 6. The center of these 6 spheres are at the corners of a regular hexagon. Hence, this packing is called two-dimensional hexagonal close packing. If we compare square close packing with hexagonal close packing, we will observe that the empty spaces are less in hexagonal close packing than compared to the square close packing. Now, what are these empty spaces and what role do they play in packing efficiency? The empty spaces in between these spheres are known as voids. These voids are responsible for decrease in packing efficiency of the solid crystal. More the number of voids, less will be the packing efficiency. Coming to the close packing in 3 dimension, first let us see the 3-dimensional close packing from 2-dimensional square close packed layers. This type of packing is obtained by placing 2-dimensional square close packed layer above the first one, such that the sphere of the second layer are exactly above the sphere of the first layer. In this arrangement, the spheres of the both layer are perfectly aligned horizontally and vertically. On arranging layers one after the other in this pattern, we will observe that each sphere is in contact with 6 other spheres, 4 from the same layer, 1 from the layer above and 1 from the layer below. So, the coordination number is 6. If we call the first layer as A type, and since the all layers are also the same type, this kind of arrangement is known as AAA type of arrangement. On observing carefully, we will find that this arrangement has generated a simple cubic lattice and its unit cell is primitive cubic unit cell. Now, we shall see the dimensional closed packing from two-dimensional hexagonal closed pack layers. Here, the three-dimensional hexagonal closed pack structure can be obtained by placing two-dimensional hexagonal closed structure one layer above the other, that is, placing the second layer over the first layer. Let us take a two-dimensional hexagonal closed pack layer A. Notice this layer has a triangular void. Place a similar closed pack layer such a way that the sphere of the second layer are placed in depression of the first layer. As the sphere of the second layer are aligned differently as compared to the first layer, so let us call this layer as B type. On observing, we will notice that not all the triangular voids of the first layer are covered by the sphere of the second layer. This gives rise to a different arrangement and a different void. Now, let us place the third layer over the second layer. Stacking of third layer of over the second layer can be done in two ways. First, by covering tetrahedral voids, second by covering octahedral voids. Before placing the third layer, let us discuss the two types of voids. There are two types of voids, tetrahedral void denoted by T and octahedral void denoted by O. Let us study how these voids are formed. When we place the closed pack layers in the depression of the first layer, we will notice that at some places the triangular void of the first layer are being covered by the sphere of second layer. At such places, the type of void is formed is known as tetrahedral void. T. Since a tetrahedron is formed by joining the center of the four surrounding spheres, while at the other places we will notice that the triangular void of the first layer coincides with the triangular void of the second layer, such that their triangular shapes do not overlap. At such places, another type of void is formed. This type of void is known as octahedral void O. Since an octahedron is formed by joining the centers of the 6 surrounding spheres. Now, in case we need to calculate the number of tetrahedral and octahedral voids in the crystal structure, then just knowing the number of spheres will save the purpose. Suppose there are n spheres in the crystal structure, then the number of octahedral voids generated is equal to n and the number of tetrahedral voids generated is equal to 2n. Now, coming back to the stacking of third layer. First, by covering tetrahedral voids. Here, the tetrahedral voids of the second layer can be covered by placing the sphere of the third layer over them. On doing so, the spheres of the third layer will get exactly aligned with the sphere of the first layer. So, if we can call the first layer as A type and the second layer as B type, then the third layer will also be A type. As the pattern of the sphere is repeated alternately in other layers, so this pattern is known as AB-AB pattern, and the structure formed is known as hexagonal closed pack HCP structure. In this type of structure, each sphere is in contact with 12 other spheres, 6 from the same layer, 3 from the bottom layer and 3 from the top layer. So, the coordination number is 12. Next, by covering octahedral voids. Here, the octahedral voids of the second layer can be covered by placing the sphere of the third layer over them. On doing so, the sphere of the third layer are not aligned with the spheres of the first layer or second layer. So, if we call the first layer as A type and the second layer as B type, then this third layer will be C type. Now, if we place the fourth layer over the octahedral void of the third layer, then this sphere get aligned with the sphere of the first layer. Thus, this pattern is known as ABC ABC type, and the structure formed is known as cubic closed pack CCP or face centered cubic FCC structure. In this type of structure, each sphere is in contact with 12 other spheres, 6 from the same layer, 3 from the bottom layer and 3 from the top layer. So, the coordination number is 12. Next, we shall see the arrangement of structural units of ionic crystal. Here, a quantity called radius ratio plays a significant role in determining the structure of ionic solids. For an ionic solid, the ratio of cation to that of the anion is called radius ratio. The structure of many ionic solids can be accounted by analyzing the relative size of the positive and negative ion. We may use simple geometric calculation to determine how many ions of a particular size can be in contact with a smaller ion. As a result, we can predict the coordination number based on the ion size. The crystal structures are determined by the coordination number of the ions. Using the radius ratio, we can predict the coordination number and the structure of ionic crystals. This table shows the relationship between radius ratio and coordination number. Now, on the basis of relative number of cations and anions present, the structure of ionic compounds are classified into types AX, AX2, AX3, A2X3, etc. Today's session, we will focus on AX and AX2 types of crystals. AX type structures, NaCl, CaCl, ZnS are examples of AX type structures. First, let us see NaCl structure. The structure of sodium chloride NaCl, or we can say rock salt structure, is made up of sodium ions and chloride ions. The unit cell of sodium chloride crystal is shown here. In this structure, sodium ions are represented by hollow spheres and chloride ions by solid circles. The silent features of this structure are as follows. The chloride ions are arranged in cubic close packing CCP arrangement. In this arrangement, Cl- ions are at the corners of the cube as well as at the center of each face, that is face centered cubic arrangement. The sodium ions occupy all the octahedral voids in cubic closed structure. For NaCl, the radius ratio value is 0.54. This value suggests an octahedral arrangement of Cl- around the Na plus ion. As seen from the figure, each Cl- ion is surrounded octahedrally by 6 Na plus ion, and each 6 Na plus ion is surrounded octahedrally by 6 Cl- ion. Thus, the coordination number of Na plus ion as well as Cl- ion is 6, that is, the structure has 6:6 coordination. Now, let us calculate the total number of ions per unit cell. Total number of chloride ions per unit cell is equal to sum of chloride ions at corners and at the face centers. The total number of chloride ions is equal to 8 corners into 1/8 per corner plus 6 faces into half per face, which is equal to 1 plus 3, 4. Total number of sodium ions per unit cell is equal to sum of sodium ions at the 12 edges and 1 at the center of the cube. The total number of sodium ions is equal to 12 edges into 1/4 per edge plus 1 in center, which is equal to 3 plus 1, 4. Thus, the total number of chloride ions equal to 4, the total number of sodium ions equal to 4. The unit cell of sodium chloride contains 4 chloride ions and 4 sodium ions. Okay, coming to the structure of cesium chloride. Cesium chloride crystal is made up of cesium ion as cation and chloride ion as anion. The unit cell of cesium chloride is shown in the figure. Cesium ions are represented by hollow circles and chloride ions are represented by solid circles. The main features of CaCl structure are: it has a body centered cubic lattice, that is BBC arrangement. Here the chloride ions are present at the corner of the cubic lattice, while cesium ions present at the center of each cube. The radius ratio is 0.943. The value suggests a cubic arrangement of Cl minus ion around the cesium ion. Here each cesium ion is surrounded by 8 Cl minus ion, and in turn each Cl minus ion is surrounded by 8 cesium ion. Therefore, the coordination number of cesium ion and chloride ion are 8:8. Now, let us calculate the total number of ions per unit cell. Total number of chloride ions per unit cell is equal to chloride ion at corners, that is, the total number of chloride ions is equal to 8 corners into 1/8 per corner, which is equal to 1. Total number of cesium ions per unit cell is equal to cesium ion at the body center. The total number of cesium ions is equal to 1 into 1, which is equal to 1. Thus, the total number of chloride ions is equal to 1, the total number of cesium ions is equal to 1. The unit cell of cesium chloride contains 1 chloride ion and 1 cesium ion. Next, crystal structure of the type AX2. First example is calcium fluoride, CaF2. Calcium fluoride is a solid and has a cubic closed packed structure, CCP. The unit cell of calcium fluoride is shown in the figure. The calcium ions are represented by hollow circles and fluoride ions are represented by solid circles. The radius ratio of calcium fluoride is 0.75. The value suggests a cubic arrangement of F minus ions around the Ca2 plus ions. Here the Ca2 plus ions are arranged in CCP arrangement, so that in the cubic lattice calcium ions are present at all the 8 corners and 1 each again at the center of the 6 faces. The fluoride ion occupy all the tetrahedral voids. Since there are 2 tetrahedral voids for each Ca2 plus ion and F minus ion occupy all the tetrahedral sites, there will be 2 F minus ion for each Ca2 plus ion. Thus, the stoichiometry of the compound is 1:2. And we can see in this arrangement each F minus ion is surrounded by 4 Ca2 plus ions, whereas each Ca2 plus ion is surrounded by 8 F minus ions. Thus, the coordination number of Ca2 plus and F minus ions are 8:4. This structure is adopted by a large number of fluorides such as BaF2, SrF2, PbF2, CuF2, HgF2, etc. Now, let us consider another example, sodium monoxide Na2O. It has anti-fluoride structure which is opposite to the fluoride CaF2 arrangement. Here the anion O2 minus adopt cubic closed pack or CCP, that is face centered cubic arrangement, whereas the sodium ion occupy the tetrahedral voids. So, we can see here in the anti-fluoride structure, the positions occupied by the Ca2 plus cations are now occupied by the O2 minus anions, and the Na plus cations occupy the position of F minus anions. That is, the occupancy is reversed, and this gives the name to the structure as anti-fluoride. The main structural features of Na2O are: the unit cell is CCP, O2 minus ion occupy all the 8 corners and also 6 face centers. Thus, in the resulting structure, each Na plus is surrounded by 4 O2 minus ions and each O2 minus ions is surrounded by 8 Na plus ions. Thus, the coordination number of Na plus and O2 minus ions are respectively 4 and 8. In this anti-fluoride structure, that is, the structure has 4:8 coordination. The Na2O unit cell consists of effectively 8 Na plus and 4 O2 minus ions, that is 4 Na2O formula units. Examples of other ionic compounds which adopt the above antifluoride structure are Li2O, K2O, Na2S, K2S, etc. So, with this I am concluding today's session. Today we have discussed different types of solids, classification of crystalline solids, crystal lattice, unit cell, close pack arrangement in crystals, followed by the structure of ionic crystals of the type AX and AX2. Hope the concept on solid state I have taken so far is clear for you. Thank you.